Hi Hannah, just a quick word or two on the scalar triple product. So here's my best possible parallelepiped. I've got an origin at vertices at A, B and C like that. So we should check that we're all happy that A dot B is mod A, mod B, cos theta. Let me put a theta in here, where little a and little b are the position vectors of capital A and capital B, and of course we prove that basically you just stick in the coordinates of A, B and C, of A and B, and you find this length using the cosine rule, and algebra follows, and out comes this thing. And then you also know how to define A cross B, and you can see algebraically that A cross B is going to be perpendicular to A and B, so let's draw A cross B coming up there. And can we see algebraically what the magnitude of A cross B is? Well, okay, so what you have to do is basically work out the magnitude of A cross B squared plus A dot B squared equals magnitude of A squared times the magnitude of B squared. So again, this is like, actually it's not as bad an algebra bash as you might imagine. So you check this by coordinates or whatever, and then that allows you to discover that mod of A cross B is mod A mod B sine theta, which we knew before anyway. And this has a pleasant interpretation because it shows that the length of A cross B is the area of this parallelogram spanned by A and B. Okay, so what about the vector triple product? Well, the scalar triple product is where you do A cross B and you dot it with C. So what that's doing is it's taking the magnitude of the red vector times the magnitude of C times cosine of the angle between them, which I guess we'll call phi. Now, if you take, what is that? Well, that's equal to well, what is mod C cos phi? Isn't mod C cos phi this green length here? That's a sort of projection across. So mod C cos phi, sorry, I should write this as mod A cross B times mod C times cos phi. But that's the base area of this parallelepiped times its perpendicular height. So this is the volume of the parallelepiped, and kind of by definition of what a matrix is, the matrix M equals AX, AY, AZ, BX, BY, BZ, CX, CY, CZ is exactly the matrix that transforms the unit cube into this parallelepiped. So the triple product here is the volume scale factor, so that's the determinant. This also, just by the way, gives you like a really cool way of thinking about how you invert a matrix. If I want to find an inverse matrix, I wonder if I can move this. Oh, hurrah, it worked. Okay, cool. So if I want to find the inverse of this matrix M, I need to find another matrix which, when I multiply by this matrix, I get something with a load of zeros in it. So multiplying by a matrix, see if I can get this right, multiplying two matrices together is a bit like taking the dot product of the respective rows in the first matrix with the respective columns in the second matrix. So if I want to get in my multiplication some zeros here and here, I need to have the first row in this matrix as perpendicular to column B and column C. So that's easy. I'll just fill in B cross C. And to get zeros here and here, I need to make sure that the second row of my, going to the inverse matrix, is perpendicular to column A and column C. So that's going to be C cross A. You have to be a bit careful to make sure you do it in a sort of cyclically consistent way to make sure you don't get weird minus signs. and then finally the last one is going to be to ensure these zeros, you get A cross B. So it's kind of semi-obvious that when you, excuse the Pauling notation, this B cross C here obviously means you work out what B cross C is, and you take its components and you transpose them and you put them in the first row. So it's kind of obvious from the fact that the cross product has these perpendicularity properties that when you do this calculation you get all of these zeros. What's really cool is that in the last case, in this sort of pink spot, what you get is B cross C dot A, which is exactly another form of this triple product. So all of these kind of pinky entries end up being this scalar triple product. So all of them are in fact the volume of the parallelepiped, so they're all the determinant. So then if you want to find the inverse, all you need to do is take this blue matrix and divide by the inverse, by the determinant. Hope that helps. Have fun.